Hello everyone. Yes, I am AI, but I am here to talk physics. All students have now completed their first physics laboratory, and most groups have submitted their work on Moodle. They will begin receiving feedback from their tutors very soon, certainly before they need to submit their second report. In the meantime, because some students require feedback before beginning the second report, it is important that they receive some comments now, even if these are generic. To give the students a sense of what a good but not perfect report looks like, we will now review and mark one together. However, before examining this report page by page, there is one very important general comment. A number of students submitted reports clearly based on templates from previous years. The instructions and requirements change every year. Using an old report as a model constitutes academic misconduct. It also leads to the inclusion of unnecessary material, such as graphs not required this year, as will be seen in this example. The students' work must be their own and must be based on the current lab manual. This is a serious issue. Having said that, the report about to be analyzed is actually one of the stronger ones and serves as a good example to learn from. It scored around 80 out of 100. We will use it now to examine what works well and what can be improved page by page.
Abstract, Objectives, Introduction. Abstract. This abstract is excellent. It is concise, complete, and written in the correct scientific past tense. It successfully summarizes the objective, method, and key result. However, a common issue appears immediately. The final result is reported as G equals 10.56 plus or minus 0.36 meters per second squared. While not mathematically incorrect, the uncertainty should be rounded to one significant figure, or two if the first digit is a 1. Here, 0.36 should be rounded to 0.4, and the mean value rounded accordingly to give G equals 10.6 plus or minus 0.4 meters per second squared. This avoids a false sense of precision and aligns with the standard used in this course. High-precision experiments may justify two significant figures in uncertainties, but first-year lab precision does not. Under no circumstances should an uncertainty exceed two significant figures. No marks were deducted for this issue. Note that in this instance, the omission of the formula is not considered an error, since the students stated that they were exploring the relationship between T and L, which determines the relationship experimentally without presupposing the theoretical expression. Objectives. These are clearly and concisely stated. Minor formatting inconsistencies, such as spacing, should be avoided. Introduction. The text is appropriate. The figure is clear, though it contains a theoretical flaw in the free body diagram. The resultant force is shown as tangential, which is generally incorrect. Except at the lowest point of the swing, the resultant force has a radial component, providing centripetal acceleration. However, at the position of maximum displacement, the speed is momentarily zero. So if the figure is meant to depict that moment, the diagram would be correct. Given this ambiguity, no marks were deducted. Page 2. Derivation and linearization. The derivation is mathematically sound and correctly leads to the linearized relationship T squared is proportional to L. However, a key theoretical detail is missing. The small angle approximation sin theta is approximately theta is valid only when theta is measured in radians. This is crucial for rigor in the theory section. Page 3. Assumptions, apparatus, procedure. Apparatus. The list is complete and precise, including all necessary details. Assumptions. While all relevant points are listed, they are presented as a long, numbered list. A professional report should condense these into descriptive paragraphs, avoiding repetitive phrasing such as, assume that. The physical relevance of each condition should be explained. An inconsistency appears. One assumption states instantaneous and accurate timing. Yet the later uncertainty analysis correctly accounts for human reaction time, contradicting that assumption. Procedure. The procedure is written as a list of instructions. A lab report should instead describe what was done in flowing paragraphs using the past passive voice. For example, the length was measured, rather than we measured the length. The experiment must be reproducible by reading this section. Page 4. Results, data tables. The table layout is good, but significant issues remain with precision and presentation. The t-squared values contain too many significant figures, implying false precision. If t has 4 significant figures, then t-squared should also have 4, i.e., 3 decimal places here. In Table 2, uncertainties must follow the rounding rules previously described, no more than 2 significant figures. Consistency is essential. The plus or minus symbol should not appear in every uncertainty cell. The column header already indicates that these values are uncertainties. The equation of the best fit line is a primary result and must be stated and interpreted explicitly in the text, not only on the graph. The r-squared value is also a primary result and must be stated and interpreted clearly. Page 5. Graph and uncertainty analysis. Graph. The graph is high quality, but the y-axis labels contain too many decimal places, cluttering the graph and suggesting unrealistic accuracy. The scale should reflect the true measurement precision. Uncertainty analysis. This section is very good. Uncertainty propagation is applied correctly. The final value of g is properly rounded here, 10.6 plus or minus 0.4 meters per second squared. This standard of rounding should appear consistently throughout the report, beginning with the data tables. Some of the calculated sample uncertainties have far too many significant figures. Page 6. Discussion. Part 1. The Excel output is well presented. The discussion of the y-intercept is satisfactory, but should go further. The confidence interval should be stated explicitly, noting that it contains 0, and the implied offset length L0 could be calculated to comment on its physical significance. The analysis correctly identifies that the experimental y-intercept 0.04 plus or minus 0.07 seconds squared is statistically compatible with 0. This is important. It indicates no statistically significant evidence of a constant systematic length offset. The discussion should emphasize this clearly. Because of this, the later claim that the cylindrical bob caused a length overestimation and thus a larger g is weakened. If the intercept is consistent with 0, then a constant systematic length offset is not supported by the data. This does not prove that no systematic effects are present, but indicates that any constant offset is too small to be detected by this experiment. At the bottom of page 6, the report uses the r-squared value appropriately to support model validity and then correctly calculates the percentage error in G. This is well done. Page 7. Discussion. Part 2 and conclusion. Discussion. Continued. A clearer distinction between random and systematic uncertainties is needed. The analysis of possible conical motion must also be physically correct. The suggestions for improvement using a spherical bob, a vernier caliper, and a laser photogate are excellent, specific, and relevant. Conclusion. This is strong, but it should explicitly mention the key finding that the y-intercept is statistically consistent with 0, providing a more complete and nuanced summary. Page 8. References and Appendix. Introduction. References. The format is correct and complete. Including references is essential for credibility and for avoiding plagiarism. Appendix Introduction. This section correctly introduces the sample calculations. Note that the standard Harvard in-text citation format is Foe and Godolphin 2019. Page 9. Appendix. Sample calculations and extra graph. The sample calculation formulae for t squared, and their uncertainties are clear and demonstrate a strong understanding of the mathematics. However, the tables again suffer from inconsistent significant figures, as seen in the main text. This page also illustrates the initial warning. A second graph comparing measured data to an ideal theoretical line, Figure 4, was not required this year and appears to come from older templates. It is better to perform a single linear regression on the experimental data rather than comparing each measured point with its theoretical value. A point-by-point comparison can be misleading. It may suggest that the model fails when the difference is actually due to a systematic effect, such as an offset in length measurement or reaction time. A single regression allows these systematic shifts to be revealed and quantified through the intercept and residuals, showing how the data deviate from theory rather than simply that they do. This makes the analysis both statistically sound and physically meaningful. Final summary. In summary, the report contains many strengths but still shows issues in uncertainty reporting, the discussion of uncertainties, and the qualitative interpretation of results. Students must ensure that their work is entirely their own. For future reports, they should focus on a professional scientific writing style, consistent handling of uncertainties, and a critical, physically grounded discussion of results.